Okay, we'll get started. In this section, we're going to be going through nuclear physics, which is 9G. So nuclear physics, that's basically we're going to be looking at the physics of really small things. So we're going to be looking at the atomic level, basically. So the first thing with this is we're going to be thinking about radioactivity. So I'm sure you've heard that word before, radioactivity. And what radioactivity is, it's the phenomenon of like a stable atom. It's a stable atom. Let's draw this as the atom, nucleus, and there's maybe some electrons around it. Great. So it's the phenomena of unstable atoms ejecting particles or energy in order to become stable. So this is the unstable atom, and what's going to happen is that unstable atom is going to eject particles. So it could eject maybe, I don't know, a proton or a neutron, or it could be ejecting just energy. And it's going to do that in order to get to a more stable state. So we call that radioactivity. So there's three main types of radiation or radioactivity. So the first type of radiation, it would be alpha radiation. The second would be beta radiation. And the third one is going to be gamma radiation. So we'll go through each of those three types of radiation. Alpha is the ejection of alpha particles. So an alpha particle is really a helium nuclei, or it's one helium nucleus, or several of them would be helium nuclei. So what that is it's really two protons, write them as positive charges, and then two neutrons, which technically don't have charges. And those, it's basically an atom's ejecting those out. It's ejecting the helium nuclei out. So that's what alpha radiation would be. You'd have basically lots of these right here. Beta radiation is a little bit different. That's the ejection of beta particles. So instead of like a nucleus that's made up of protons and neutrons, that's going to be just free moving electrons that get ejected. So again, still a particle, but a little bit different. And then the last one, gamma, that's the ejection of high energy photons. That's technically, the way to think of it would probably be gamma rays, so you've seen that before. So again, high energy electromagnetic radiation. So those are the three main types of radiation. And they're ranked from lowest to highest energy. So alpha is the least amount of energy, beta is in the middle, and then gamma is the most, or the highest energy. And if one last thing to kind of keep in mind, the exposure to radiation, it's not good for living things. That can lead to radiation sickness, which is possibly fatal. So again, cells, okay, that's a cell. Basically, when they're hit with radiation of any kind, it could be energy, it could be like particles that are being ejected. When it's hit with that, what it does is basically alters the cell in ways that aren't good for it, and that can cause illness. So that's the first kind of ideas about what's radioactivity, what are the major types. Now we're going to be looking at two specific radioactive chemical reactions. So again, chemical reaction where you would have radioactivity taking place. You'd have the ejection of either energy or these kind of fast-moving particles. So the first chemical reaction we're going to look at is nuclear fission. Nuclear fission. And this chemical reaction is when you have high mass atoms that are split into two parts by absorbing a neutron. So it's basically you have an atom and you shoot a neutron at it, and what happens is that atom breaks into two pieces. That's effectively what happens with fission. And then what happens really, in some cases, you're gonna have this when it breaks apart. These particles, basically, some of the neutrons from these particles are gonna hit other large atoms, and then they're gonna split into smaller pieces. And then you end up getting this kind of chain reaction, basically. So again, that doesn't happen always, but that's what happens sometimes is basically you get this many, one atom gets split and then that keeps going and going and going. And when this happens, basically if you get nuclear fission, and especially if you get a chain reaction, you get a huge release of energy. So again, if you ever got a chain reaction like this where you have, one atom splitting and then it splits another, that's a very large amount of energy, and that's governed, the amount of energy that's released in a nuclear reaction like this is actually governed by E is equal to mc squared. I'm sure you've heard that before. It's basically saying the amount of energy released in a reaction like this is equal to the mass that's basically gets converted to energy times the speed of light squared. So basically what this says is if you have mass, you're taking whatever mass is converted into energy and you're multiplying that by the speed of light squared. So it's basically anytime you get a reaction like this and you're losing some mass, it's an enormous amount of energy. That's what this equation basically says. And again, so again, for that reason, nuclear fission you'd use in nuclear power plants and a nuclear weapon. That's really what's happening is you're basically taking a little bit of mass and you get an enormous amount of energy. That's what makes these things possible. And the other kind of, now we're going to look at the other kind of companion reaction to that, the other type of radioactive chemical reaction. That would be nuclear fusion. So it's kind of the opposite. So that's what happens when two low mass atoms combine into a higher mass atom. And what's an example of this would be if you have deuterium and then it combines and then you're getting helium out of that. That's kind of a more common example of nuclear fusion. And nuclear fusion, the big thing to keep in mind is this, even though you're putting stuff together, you're actually basically releasing energy, just like in fission. And you're getting a lot of energy that's coming out of this process. And nuclear fission is what creates heat. Creates heat, not just heat and light in the sun. So again, both of these processes, enormous releases of energy. They go, one's basically breaking down something, one's basically building up something. But either case, you are getting radioactivity. You are getting a huge release of energy, and the motion of, ejected particles as well. So that's really all of the stuff for nuclear physics. Keeping in mind what is radioactivity, and then what are two very common nuclear reactions or radioactive chemical reactions, you could think of them. Okay, so we're going to see a problem out with this. Where is it? Right here. Here we go. So again, make sure you take an attempt at this problem before I go through it. Make sure you're not playing Flappy Bird. Okay, so what do we have here? We have some plutonium, great, split into smaller atoms. During this process, 1 gram of the original plutonium is converted into energy. So let's draw this out, might be helpful. So we have some plutonium. I'm just gonna draw it. It's a large. I don't know. It's a bunch of plutonium atoms, and it's saying okay, it's getting split into smaller atoms. And then you're also basically releasing energy from this. And it's saying basically 1 gram of that mass of plutonium is getting converted into energy. So the first thing it's asking is this fission or fusion? Nuclear fission, nuclear fusion. This would be an example of nuclear fission. The explanation for this would be the atom, plutonium basically. There might be several atoms, but you get the idea. So the atom is being broken down to release energy. Release energy. So that's the idea basically. You're taking something, a larger, plutonium atom, and it tells you explicitly it's being broken down. That's nuclear fission. So how much energy is released from the plutonium? So we got to think about that. We know the mass that gets converted into energy ultimately is 1 gram. 1 gram, or we could also think of that as 0.001 kilogram. And we're looking for the energy that's released as a result of that. So again, some of it goes into being just broken into smaller pieces, and some of it goes to energy. How much energy is that? So we're going to use the equation E is equal to mc squared, where E, the amount of energy, is going to be equal to the mass, which we know, times C, which is given. It's 3 times 10 to the 8th. And then that's going to be squared. So we just got to multiply this out, and it's going to be 9 times 10 to the 13th joules. And again, this is a huge amount of energy. This is in scientific notation. Usually we deal with maybe thousands or hundreds of thousands of joules. This is a very large amount of energy. And it's because you're multiplying it by c squared. C is very big itself. So that's the amount of energy. And then the last thing is how much power. How much power does this process exert if it happens in 1 times 10 to the negative 6 seconds? That's a microsecond. So if we think about power, this isn't electrical. So this isn't really an electrical process. There's really only one way to directly calculate power. That's going to be the work divided by the time. We know the work, or we know the amount of energy released, and we do know the time. So it's fairly straightforward to get the power out. So I'm going to put in the amount of work, 9 times 10 to the 13 joules. We're going to take the time, 1 times 10 to the negative 6 seconds. Make sure if you're punching a calculator, you put both of these in parentheses. Would be a good idea. And then we get that it's gonna equal 9 times 10 to the 19th watts. So that's the amount of power that's exerted in this process. So that's about it for this section. Make sure you have all of it copied down, including the problem, and that's about it for now.